form, and let us say this contains one information about the one trace, and then we want to add that another trace to remove some noise to enhance the signal. So in that vector space we can add, say, s plus t is another that can be expressed in terms of, say, s1 t1 s2 t2 s3 t3 up to s1000 plus t1000, and this is a notations we followed, and that is useful in some of your applications in storage and operations. Hilbert space is another space where some of the properties which await in the linear algebra, and these are the properties. Say, let us say that there are two vectors, x and the y, and there is a real numbers, say x and the y. They have been defined in a Cartesian coordinate systems. So the dot product is defined by, say, x1, x2, x3 into y1, y2, y3. We can express, say, x1, y1 plus x2, y2 plus x3, y3 like that. So they obeys the three properties. One is the dot product. That means it is a symmetric in x and y. So x into y equal to y into x. It is a linear, it is the first arguments, and that way you can write it, say, x1 plus bx2 into y equal to x1 y plus bx2 y, where a and the b are the scalars and x1 and y1 is the vectors. And it is a positive definite for all vectors. That means x into x transpose, so let us say it is greater than equal to 0. With this forms, we have the applications. It is extensions of your vector space. So these continuations.
Vector space and
the Hilbert space. So Hilbert space is a vector space, but three certain properties are obeyed. One is inner product. So suppose if you want to measure the angle between the two, say x and the y. So x dot y equal to x into y cos theta. So theta is the angle between the x and y. That theta can be estimated. So it is a inner product or the angles. If you want to measure it, then we should actually exploit the properties in the Hilbert space. But it is a extension of your the vector space. But three extra properties that we have discussed. One is that the first one, that it is a symmetric in x and y. So x into y equal to y into x. This operation is obeyed. It is a linear. This is first argument. So x1 plus bx2 equal to x1 y plus bx2 y. A and b are the scalars, and x and y are the vectors, and it is a positive definite. And so this dot product, it satisfies three properties known as the inner product. So this is specifically useful for your Hilbert space domain definition. Median space, I don't have idea about that median space. Euclidean space. Oh, Euclidean space is a space where that equilibrium geometry, like suppose if you want to measure the distance between the 2 points. So that can be measured in the formula. It's a distance measures law, right? So suppose we define a Cartesian coordinate system, say x, y, and z, and we are defining some points in the space, which is represented by, say, x1, x2, say x1, y1, z1. Then another point, say x2, y2, z3. Now we want to measure the distance between the two coordinates. Then we use the distance between the two coordinates. So distance law is follows, like square root of x1 minus x2 y1 plus square plus y2 minus y1 square plus z1 minus z2 whole square. So there is a Euclidean space is there where Euclidean geometrical rules are follows to measure the distance, and it has been used for your different classification schemes to define the norms when we say that what is the distance between the 2 points. So let us say we are saying that we have our model parameters, we know the physics, we predict the data, say D. Now we have the observations, say D observed, and we have we predicted a point, say data D. Now how close this D predicted with the D observed? So if you want to measure the distance between these 2 points, then we need to find that what is the distance between, say, Y, means data predicted, and the data observed. And here data predicted and data observed, they have been at 2 points in a, say, Euclidean space. The 2 points are denoted by the coordinate system, say x, y, z. Right. Now we want to measure the distance, and now when your predictions is very close to your observed, obviously 2 points overlap. That means the distance between the 2 points is 0. So basically this norms is defined, it is actually the distance between the two, where we form that it is L1 norm or L2 norm. So L1 norm is the distance between the two. What is the distance? It is the distance defined by, one is your predicted data point, another is the observed data point, which is actually presented in a coordinate system. And this is a measures that when this distance is 0, ideally we say that our prediction is equal to your observation. That means our theory is perfect for predicting the data. So this distance can be measured in a different form. Either you can measure it just absolute difference between the two coordinate system, or you can measure it is a square root of the, say it is called it is a L2 norm. No, Hilbert space is a specific space where some of the properties we want to use it for your operation purposes, then it has been used. It is not that inverse problem always has to be solved in an Hilbert space. Okay. So that this norm, which is actually defined, that it is a functions from a spaces of vectors onto a scalars, and it is denoted by these notations called that norms is denoted by this notation. These are two vertical bars pointed by this circle, and this is obeys that. So let us say there are two vectors, say u and the v, and there are other scalars, say alpha is another scalar. Then these norms obeys these properties. One is that these norms of v should be greater than 0, and any multiplication of your scalar with these norms should be operated by the just multiplication into the norms, and it also follows the triangle laws. That means the sum of the two sides of your triangle should be greater than equal to the third one, like that. So u plus v is less than equal to individual u and the v. U and the v are the two vectors, and we can define that these norms, say x norm, L is the order, P is the order, X, L, P. P is the order of the norm, and it is equal to the summations mod of xi. So xi to the power p whole to the power 1 by p. P is the order. Now this is a expressions for your norms. Okay, now if you increase this, change this value p, then order will change. Now the condition is that p cannot be less than 0. P cannot be negative. So order cannot be negative. P always greater than equal to the 0. So P can be, the order can be from 0, 1 to infinity. Right. Now if we put this P is 1, it is L1, P is 2, L2, like that. And we are talking about that L2 naught. So P, if we put this P is 2, then X2, the norm is, it is a square root of X transpose X. Here you see this X is actually your error, let us say. X is, the error means E equal to D minus GM. D is your data, observed data, GM is the predicted data. and the difference between the observations and predictions is your E. So that will be your, like that, E transpose E, like that. So L2 norms is that it is the difference between the two observations and predicted to the power, it is square and square root, whole to the power 1 by 2. Now let us say that what type of norms we should use it. Now if you use this P from 1 to say 2, 3, 4, 5, then the distributions of this value will see that it shows this, it is a exponential. This term is a double exponential. You see how the P is varies. If you say this P is 2, it is actually your L2 norm. Where P is 10, L10 norm. Now, if your data, say for example, follows the Gaussian distribution, it is a bell-shaped, then it is recommended that it will be more stable if you use this norm is 2. So if your data distributions or noise distributions in your problems follows the Gaussian, then it is recommended to use this norms is P2, that means L2 norm. That is because you see this is actually follows the bell-shaped curve or the Gaussian distribution, and it is a more stable in that case. And if your data distributions and noise distributions, say let us say, or noisy data distribution follows this double exponential, so in that case it is shown that this P, if you take is 1 or the L1 norm, it will be the more stable. So in terms of stability, if we answer it, then if you want to see that it is a double exponential distribution, then we should go for the L1 norm. And if it is a normal cases, normally distributed the Gaussians, then we should use it, the norm 2.
Can you give some examples of the physical scenarios that they may illustrate what we are speaking of?
The distribution.
Geophysical scenarios.
Actually, geophysical scenario.
That they do elaborate maybe some data may be behaving in normal distribution or wave motion and some sort of that kind.
Okay. So you are saying about that with this data, how we can say calculate this type of norms. So given a data, we want to calculate the norms. We want to say this one, or in a particular scenario, which type of norms in a field case we should use it.
What I mean to say, sir, you have said some data may behave with like normal distribution, Gaussian, and so forth. So my issue is to get some example of geophysical scenarios which their data behaves in this context.
Okay. So let us say that X is your, say, let us say one time series or a data you have collected along a profile, right? So it is a profile, say any readings of your data. Now you put this the Gaussian normal distribution of that data, right? If this normal distribution of this data follows the mostly these Gaussians, then in that cases you see your data or even data with if some amount of noise is there that follows the normal Gaussian. So in that case, your recommended thing is that we should go for the L2 norm. P value is the order. P is the order of your P is the order. So if you change this P value, then this distribution, theoretical distribution will change. So this is a theoretical expression which is given. So if you change this P value, we will get this type of array of your distribution. How to determine the P value from the data? So in this case or not, in normal distribution, it is not the P value is there. Normal distribution means the Gaussian distribution. In the formula, it mean is required, right? median variance is required, and that will follow this way. Now using these expressions, you plot this one. If it mostly follows, most of your data point follows the normal distribution, that means if it is your noise is also there, it will follow the normal Gaussian. So in that case, it is just safe to use this type of L2 norm. So in case you will see this, some outliers are there, and it is not fitted with the normal curve, and you may get this type of only exponential, maybe double exponential, maybe another curve. So in that case, it is actually recommended that this is a theoretical curve has been produced. Say suppose p is 1, then your exponential double exponential curve should come. But if it is not with your real data, then we can cross check it to start with, right? So this is actually gamma functions distributions and the stability, that which type of norms is actually follows with this expression. This is a gamma functions expression. So here you will see this, the expression of the different norms. L1 norms, it is the absolute difference between the 2 points, observed versus predicted. L2 norms, it is the square terms are there, mean square error, and so on. So mostly we use this one depending upon the two things. One is that outliers on the noise component, and second is the stability. Stability, last slide we have discussed about that. If your data is actually double exponential distributed, then the P1 norm is more stable than the P2. If it is a Gaussian, then we should go for the normal Gaussian or L2 norm. And here you will see this. So it is the absolute difference between the 2 points, where it is the square terms. So if you see that your data is perturbed by the outliers, then your L1 norms, the absolute based method which is derived, it will be more stable than the L2 norm. This is another way you can check it, that whether you should use it L1 or L2 in terms of your outlier tackling. And these curves, in some of your previous slides, you already discussed that how we can get it, that outliers and their fittings is calculated, and from that also it is seen that how it is depends on the layer. Say suppose your data distribution is have an outliers, then the Gaussian probability distributions, your y axis is the probability distributions. So that probability distributions, you can say that it is a long tail or the short tail. From that also you can understand that the type of the outliers is present in the data, or what type of noise we should actually, what type of norms we should consider for your data analysis. So when we are talking about the noise and the selection of the norms, there you will see that it has been practiced for long back. When we are doing this inversion problem, since that try to find out the internal structure of the galactic bodies in space. So that time also people used to use these inverse methods. And here the two types of algorithm has been used. One is that minimizing the sum of the values of the misfit function. That is called the least absolute values method. And essentially you see this has been actually practiced by the Boscovich in the Laplace. And there is another school of thoughts which is called the Legender and the Gauss. So here actually minimizing the sum of the square values of the misfit. And that way you see this first one actually denoting your L1 norms, which is based on the absolute base method. Second one is the L2 norms, or the, because it is minimizing the sum of the square values of the misfit function. So this type of practices actually follows two types of approximation. One is that Laplacian distribution, another is the Gaussian distribution. So when your data distribution is Gaussian, usually we recommend just L2, and the absolute and the data distribution is actually which outlier is there. In that case, it mostly actually governed by the Laplacian. And there is a popularity of the use of your least square methods with the linear algebra. The least square methods or L2 norm is based on your linear algebra, whereas the least absolute based methods or the L1 norms, it is based on the LPP. And depending upon the outliers, it has been shown that, or it has been recommended that the absolute based method is far more stable in compared to the L2 or the least square based method when the outliers is actually concerned in your data. So this is what about that the matrix inversions and how this damping is actually involved in your to obtain the stabilized solutions, and the type of the noise which may encounter your observations, and when you know that the noise is, the types of the noise is known or to be known, so in that case what type of norms we should use it, and then what are the some of the formulas or the expressions has been used in your Hilbert and the vector space. That is what our the summary of this talk. Now we will pardon?
L1 norm is equal to equivalent compared to L2 norm. Then get on the linear problem. So by seeing that the previous figure, like the double exponential and
Gaussian.
like can we predict the L1 norm by using L2 norm, by using the combination of L2 norm and the linear norm?
Yes, there is a possibility, it's a hybrid norm. Say we can define this norm in a combination of L1 and L2. Mostly L1 and L2 norms are having practice on our geosciences because of the that most of our problems or the noise or outliers present in the data that are handled by the both the norms. But the thing is that these are coming from the two school of thoughts. One is based on your absolute based methods, another is the your square, mean square, least square based methods. And we can combine it to define so that there is a more sort of hybrid type of norm can be defined. Procedures means suppose if you want to use say optimization functions where we want to use that different combinations of your optimization. Say one is your local, another is your say global. So how we will define it? That way we can use it in a combined say part of both the expressions in a linear combinations. We give some weights and define the whole norms. One part is your L1 and another part is L2. Yes. That is what we are talking about. So here in my continuations of these matrix inversions and in the talk, here we will mostly discuss about the resolution part. So in the first talk we talked about the noise, types of the noise, then in the matrix inversions, how these least squares methods and damped least square methods are influenced by selections of your damping and other things which is actually related. Here we talked about that some resolutions, and then when we are solving these inverse problems, there are a lot of uncertainties associated with that. One is the data uncertainty and the model resolution, model uncertainty, and what type of things are attached to that. That we will discuss in that when we are solving this inverse problem. It is a one type of solving appraisal problem. So what are the uncertainty attached to that? That also we want to address it by re-estimating and things that we'll discuss, and then some part of your least squares and some influence of your regularizations theory, which is actually required to constrain the solutions in a better way. So these are the books which is recommended from where we have consulted, and these are textbooks, and the most used one is the written by the Menke geophysical data analysis, where these expressions of your vectors, the operations of your linear algebra, and these norms, what type of norms and their stability, all these issues are better explained in detail, so you can consult this, and it is available freely. And so the noise is one issue when we actually collect the data on the field. The sources of noise is different. It may be from human generated, you may be generated by, say, natural variability of your signals. It may be a power line noise. It may be a things that when we are handling the instrument, that type also noise can be generated by the persons who is operating it. So noise is a part, integral part. So no data can be a noise-free data. And in the field work, we see that the role of the noise is there. That is one of the part which is that has to be addressed in a different way. And the inverse problem again associated with that incompleteness. It have that we have a limited set of data which is acquired on the Earth's surface, but we want to address that the continuous distribution of the physical property which is varying inside the Earth. So our data may be limited, data may be incomplete. Sometimes it may happen in the field that you deployed an instrument like a magnetotelluric instrument. You deployed an instrument in the field, kept it for say 7 days, up to say 1 month. It is a long period magnetotelluric data. It records the variation of the Earth's electrical field, magnetic field, and their combinations. And that times you have that we cannot monitor it. Sometimes it happens that villagers, they disturb the deployment. So the records is stopped. So it may happen that you may miss some of the important information which is deployed in that. So incomplete data, it is another issue in the all geophysical domains. And insufficient. It may happen that we need that every point of the data on the Earth's surface to get that continuous distribution of the properties inside the Earth. But that never be possible because that is limited by the equipment and the logistics. It may happen that you are carrying out a survey, there are long, terrain came that we cannot access that area. There is a deep forest are there. So we cannot collect the data. So we have a data points from one side of rivers and another side of rivers. And we cannot, we want to fill it by interpolations like that. So, but we need to define the physical property below that point, below the forest like that. This is what are the problems we face in the data acquisition part, and the data and the noise is also another part. So that is why these inverse problems, when you are solving it, all these issues has to be taken into account for your final interpretations. So data model relationship can be a linear one, quasi-linear, highly non-linear, but there must be a relation between the models and the observation. Otherwise, we cannot start the inverse problem. So in order to start this inverse problem, first we have to know that what is the relations between data and the models. So we have to know the physics at least at the first hand. Otherwise, we cannot compute the forward response. Without this forward response, we cannot start the inversion process. What happens? We have to initialize this model, assume that hypothetical Mother Earth, compute that using the physics, compute the first forward response. Then this response has to be matched that how close it is to the observation of the data acquired on the field. Then we set up the misfit functions, loss functions in terms of using the different type of norms. Then the inversion process will start. by minimizing the error through iterative process. That iterations can be your local one, the gradient based, or it may be a iterative process using the sampling base or the global optimizers. That is how these data model relationships are there. But the problem will start that this is the ideal cases where we expect that noise can be a not very complex or statistical distribution characteristics of the noise should be known. But in many cases it has been that statistical distribution of the noise cannot be known a priori before starting the any inversion scheme. So here you will see that we start with the true models, apply the forward theory, compute the data, then if the data how it is close to your say true, then estimations problem will start, and that can be iterative based methods, and finally it leads to that optimal solution we call it is estimated. But the things will be there that estimated models parameter you have. Now how you can be sure that your model parameter has been a true one with which is actually you are looking for. So only there is another step which is required, that estimated model parameter how it is close to the true answer or the true model parameter. You may question it, what is the true? Because the estimation problems actually involves that your estimated parameters also should be close to the ideal one, and then that process is called it is a appraisal. So any processes we start with that, say let us say your first equations where the data is related to your model parameters, and so this data is related to the model parameters, and M is your say here model parameter, G is the say kernel matrix in a linear cases, where this case is we assume that there is a no noise component is there. Now if the obviously the real data is a noisy data, so in order to describe this the data model relationship, we can express that say D is your data and G is your say kernel matrix or the operators operating on the M, and E is a component that is a error or the misfit, and so from that we estimate this model M, which is the G inverse G. So this is actually generalized inverse operator operating on D, and this generalized inverse operator also acting on the error terms, and that gives that the formulations that G generalized inverse operator G M plus G generalized inverse operator on E. Now if we arrange it, that this model estimations is equal to the generalized inverse operator G minus I is your identity matrix M plus this is a generalized inverse operator operating on the noise. Now if you see this, that suppose generalized inverse operator G into G, if it is equal to the I, then this part is just equal to your 0. That means there is a effect that this estimated model parameter can be close to the true one, and there is a part called the artifacts. So because of the error in that, this part is actually in your expression. So here we are looking for the model, estimated model, how it is close to your true one, and that is also associated with that two components. One is this part, generalized inverse operator G minus I, and this is actually denoted as the part which is limited the resolutions. So this part is actually creating the blurring effect in the inversions, and the last part is actually associated to the error propagation, because error is there, and here we are operating the generalized inverse operator on the E. So these artifacts and the blurring, these are the two components it is there to express that how our estimated model parameter is equal to your true one. So if you see this, there is a no blurring, there is a no artifact in the data, then your estimated model parameter is actually your true model parameter. So mathematically we can also express that when we are start with say true models, we do not know what is the true model. So let us say any models. Start with the any models, then apply this forward problems, forward theory, predicted the data. This data is close to your observations. Then start these inverse problems. Now through these inverse problems, we get optimal solution say M. Now we want to see this or examine this, how this estimated model parameter is close to your true one, and that involves your appraisal problem. And from the expressions you see this, that if these true models equal to your estimated model, provided we do not have the blurring effect and we do not have the artifact. So artifact is most mainly controlled by the noise component is there in the data, whereas this resolution part, it is the problem with the forward theory. So in fact, if you see this, they suppose we use some forward theory, means some physics, that physics may not be appropriate for a particular problem. So in that cases, this blurring effect will appear. And that is mostly related to your resolution part, resolution of the model space.
bar equal to G energy P minus 1.
Which one are you talking about?
Actually, the second equation D equal to Gm plus E, right? If you send the things the right hand side, you have to left hand side.
Okay, so actually this E is a vector. So you can add it. You can do it is a minus. It should be minus, right? So it is not a problem because it is only the notation. No, these are not the subtraction. It is estimated model parameter. We want to separate it out with the true models with the estimated models. So this is actually the true one. Yes. So this is actually true one. Okay, so notation. True model.
How do we get the true model?
True model actually God knows which one is the true model.
Let me tell you.
We know that there is some idealized things. Okay, but we do not know because you see the model parameters we say that is we need to validate it with the drill hole informations. So mathematical formulations and the optimizations will give you all sort of things to get the confidence. But unless and until that model parameters we measure directly by some drill informations like that, we cannot say that, okay, this is the correct solution, let us say. So we say that there is a solution which is true that may not be validated every time, right? Because if you want to know some parameters, say D path, where only we have to check it to the hypothesis, because say interior of the earth, where we cannot take the direct measurement in that day, right? So we say this, there is a true models, one reference, and we are seeing that our estimations is actually how it is related to the true, and what are the attached error actually associated with that. Because there is error due to that artifact, the noise component. But there may be an error that when you are computing the forward theory, that theory may not be the appropriately taken for that particular cases. Physics may not be well explained to the relations between the data and the models. So that part is related to your resolution part, which is actually this from the expression we can express it and to understand that what are the things are attached to this expression.
Clarity. Yes, sir. It is like this. Someone, let's assume someone has gone to field, has collected the data. Now, the confusion is like this. We are having the data from the field, and there is this thing called true model. Now, what is the source of this true model? Where is it from? And if it is assumed, that means if you are having a legal geophysicist, everyone will come with his or her own true model. Now, which model is the best and how to fit them?
So when we are collecting the data from the field, we are assuming that, say, let us say there is a noise free, case one, but no data cannot be foolproof that it is a noise free, right? Now, when you are formulating these inverse problems, so we have to first guess about that what you are expecting, your initial model is, your mother earth, say let us say in a resistivity inverse problem you are talking about, okay. So you have the observations on the earth surface, you have acquired the data along a profile, let us say. Now, from the response, say apparent resistivity with this AB by 2 or the electrode spacing, we can get some idea about that, how the apparent resistivity is changing with the depth, let us say. Okay. Now from the patterns, we can have some idea that, okay, resistivity first layer is increasing and then decreasing and like that. Now this response, from the response you can get some idea that, okay, my first initial guess should be if it is a high, so first layer should be similar to a high compared to the second. Like that you have to first hypothetically actually assume the mother earth, what should be, you have to imagine it. Okay, then the second questions will come that how many layers are there. Okay, so there is a problems of, say, dual problems that, say, combinations of your, say, thickness and the resistivity. So you can actually, there is equivalent problem is there in the inversion, potential field. So that is a issue that may not be resolved at the first hand, but you can play with this number of the layers, with this resistivity, and see how your optimal combinations is give the reliable things. But
This is our theoretical formula. Okay? Now, you learn an inversion. When you learn an inversion, okay? Can you hear me? Okay. You learn an inversion. And that inversion will give you M tilde, because that will never give you the true model. And you don't even know what the true model is. Okay? So what if you just, for D, you put in the exact theoretical model, this formula. Then what you get is this equation, right? So this is only giving you an indication that when your G inverse C is equal to I, you can get to the true model. Okay? So what that means is that this matrix, generalized inverse matrix, itself can tell you something about how well you can resolve the model. It will not give you the exact model ever, but it can tell you how well it is resolved. Okay? Yes.
The second case,
Yeah.
assume like you are having degree for geophysics.
Yes.
They all have gone through, they are collected the data and they are now back to lab and they are processing the data.
Yes.
Now, because of the instruments, they will be having almost the same data. But because of the lab session, the lead for the analysis will be having different assumptions to get the true model.
Right.
Now, how are we going to choose the best approach from the four?
Okay, so in situations like this, you have to use all solutions and then take the average and then look at uncertainty. Because what that is telling you is that you cannot get exact solution, right? And that can be done much better using statistical formulas. And we will discuss that. But the main focus in this situation, which Soren is trying to explain to you, is that we don't know the true model, but at least we can have some idea about how well we are finding the model. Okay? And that particular parameter, so how well you can find the model, can be estimated from a function of the generalized numbers. Okay? Yes? Yeah, so this is something that we're talking about the linear inverse problem here, where there is no starting solution. It's essentially doing a one step. But you can also put a prior information, which is not shown here, and that can also be implemented. So this will then be weighted least squares, so the weights are going to be on the models. Similarly, you can have weights on the data. So you can have weight on the data, you can weight on the model. Weight on the model is what you put in based on your belief in how well you know your starting model. So that will be done by weighted least squares. But this is just an ordinary least squares that he's talking about. What do you mean with true data? Oh, I think you are hitting upon a very important point, and this will be an exercise given to you. Okay? And I will give you some data. I'll give you the forward model operator, and I'll ask you to derive the models. And you will not find the answer. Okay? In the first go. Then you'll have to use some tricks. Okay? And this is what inverse theory is all about. How you can find your answer that is not the correct answer, but close to being a correct answer, given some incomplete, insufficient data. Okay? So yes, that is an important question. That's exactly what we'll do.
Thank
See, we are all right? You are problem.
So coming to the point that resolutions, so there are two types of resolutions it is associated with the analysis. One is the data resolutions, another is the model resolution matrix. So let us say in a linear inverse problems, we say that D is described by the equations G into M, G is your kernel. So using the generalized theory, we can write that model estimations is generalized inverse operators on the D observations, and now we have that, we assume that there is no additive vector, the noise in the data. So data predicted equal to, we can write GM estimated, and where the G estimated is the generalized inverse operator into D observations, and that comes out to that the D predictions equal to your G into generalized inverse operators D into D observations. So the G into generalized inverse operators is known as that N, and it is called, it is a data resolution matrix. Now this, if the generalized inverse G into generalized inverse operator, if it is equal to your identity matrix, then we can say that your data predicted is equal to your, say, data observations. And usually we will evaluate this, that how we can compute this in, and there we will see this how this matrix and the elements, how it is distributed, and that can be a useful guidance about that how your data is close to your observations, and so on. So model resolution matrix is actually defined that, let us say that M is your true model parameters. So G into M true equal to your D observations. Now the M estimated equal to generalized inverse operators into the D observations. Now M estimated is generalized inverse operator into G M true. So then the generalized inverse operator into G, this is denoted as a R M true. So R is here your model resolution matrix. So model resolution matrix, when it is equal to your identity matrix, then your estimated model parameters is equal to your true model parameters. So that way, by evaluating this model resolution matrix and the data resolution matrix, we can have some idea about that, how our estimation is close to your true one, and what are the error is associated with that. And by evaluating this, we can see that, say, data predicted is related to your data observations, and how the elements of your data resolution matrix actually has been distributed over the panel. And in the most cases, you see that D predicted is actually your D observations, and you say this is your identity matrix. That means your only diagonal elements are actually 1 and all of the off diagonal elements are 0. So in that case, your data predicted equal to your data observations. Now if there is in a practical cases, it may happens that you will get that your main diagonal elements are very close to 1, but there will be off diagonal elements that may not be all are 0. That means that your predictions is not actually truly predicted the observations. Some amount of the error is actually associated with that. So by evaluating this panel, the data resolution matrix, we can see that how the other types of error is attached to in your prediction problem. Similarly, if we see this panel of your model resolution matrix, there also we can evaluate it, that how your estimated model parameter is close to the true one. And in a process, if there is a more number of the model parameters are there, how these model parameters are actually resolved. So if it is a cases, say, identity matrix like that, so in that cases, M estimated equal to your M true. So only main diagonals will be there, and there will be no off diagonal elements in ideal cases. But in cases, it may happen that there will be some value. So this value and their distribution, how it is far from the main diagonal, that gives you that how the model parameter has been resolved it in your inverse problem. That means, say, if there is an inverse problem, in inverse problem, more number of the model parameters is there. Some model parameters are resolved, some may not be resolved it. So the how many model parameters are resolved, how they are associated it. So by evaluating the model resolution matrix, we can analyze it, or how they are related it. So from the distributions of your elements in the resolution matrix, model resolution matrix, we can able to interpret their relations, how they are resolved it, what is the relations, and at what extent they have been resolved it. So there is another approach that weighted expressions, that if you see these model estimations, it can be a combinations. So if you see this model resolution matrix, that this is your main diagonals, so some elements will be there. There may be some value along this row. There may be a value along this row. Now thing is that if it is a completely resolved, So you will get some sort of purely bell-shaped curves over that. And there will be a side lobes also will be there. Now, if we say that along a row, that how this it can be expressed it, say if ideal cases, if it is a 1, all are 0, then it is a sharply peaked at that point. But if there is a some value, and you will get the some amount of your some amount of these distributions, then from these expressions we can also understand that how our model estimations is actually related or influenced by the model parameters which is actually lying neighborhood of the particular model's parameter. So from these expressions we can say that it is expression of the weighted average. So your estimated model parameter is the weighted average of the model parameters which are lying neighborhood of the original one. So these are the two expressions which is actually comes from that. One is the least square base methods, where you see this. Another is the which is appropriate for your overdetermined problems expressions, and another is the underdetermined problem expression. So these two expressions, which is one is for your overdetermined problem, we call it is a say least square based approach. Another is this expression is comes from your underdetermined problems, and the third one is shows that there is a damping factor which is actually incorporated to give the more stable solutions in the expressions, and the last one is the expressions of the weighted average of your weighted expression. So here you see that this WE is the error, weighted error, which is also incorporated in the expressions. So one is that WE, this weighted, it is related to the error of your data complexity, and W subscript M, this is the weighted related to the model complexity. And these two terms actually combine in the expressions. So that way, this your estimated models actually giving the idea about that how our estimated model parameter is able to address the data complexity part as well as the model complexity part. So data complexity part is mostly characterized by the noise component present in the data, whereas this model, whereas the WM, it is mostly characterized by the how our physics is going to resolve the resolution, resolve the model parameters in your inverted solutions. So in order to have that the more smooth solutions, that is the weighted, one is your weighted versions, another is that this weighted solutions is comes from the using the flatness matrix. So let us say this L is a operator, L is a distance measures which can be expressed with the help of that flatness matrix say D, and which is operating on the M, and we can express this the length, say the length is the simple way to represent the complexity of your inverse problem. So this length is nothing but a distance between the observations and predictions, and this length can be expressed that in combinations of your the weighting matrix say Wm. So finally we can express this the cost functions of the length, and the weighted least square solutions can be seen that, say let us say EQ is your misfit and ET is your error, so D minus GM, and E is your normal error, D minus GM transpose, and WE is the weighted error which is associated to your error associated to the data. So here we can express say D minus GM transpose WE D minus GM, and finally we can get it that expressions, and by solving this, the first derivative equal to the 0 and get that estimated solutions, there you will see that estimated model parameters, it is a combination of that weighted error. So this weighted error incorporated in between G transpose G, and it is also there in the next part. So this weighted error is actually that gives some of the smoothness your estimated model parameters. So smoothness is the one way to address the non-uniqueness in your inverse problem. So this is your expressions of your minimum length solutions or weighted minimum length solutions. Here your length or the say can be expressed that m is your model parameters and m to the power ap is your say prior knowledge about the model parameter, and this gives you that measures that m minus mp whole to the power transpose wm is the weighting matrix, and this is a normal. So this is a one way that we are thinking about that. So when we are inverting the solutions, when you are doing these inversions, the solution how it is a reliable. So let us say that in many inverse problems we start with say infinite number of solution in a large bound. So it will lead up to the huge computations for that. So in that case, this prior state of informations can be very useful to start with the initial, and that can give you the expressions about that how our model estimated can be provided in terms of your prior state of informations of the model parameters with the associated expressions. Okay, so we have talked about the least squares in the lectures, and so here we will see that in the resistivity inverse problems they are. So this is our observations where this is your forward theory, and this is the inverted solutions which has been obtained with the help of the singular value decompositions of your G matrix, and finally we can have that idea about that by changing your damping factors, say beta, we can control these solutions and get a more stable solution. So we will discuss this in some of your tutorials on the examples when we will talk about the resistivity inversions, that how this beta have a role to fine tune these model parameters. Okay, so I will conclude here my talk.